There's binary and there's analog, yes. Okay. Analog is a signal, like an audio signal might look like, well, pure tone would be like, right, like a sine wave, right? But if you have some other tone, right, and you saw this on the oscilloscope, it could be, right, some crazy thing like that, right? Okay. Now, we can represent this, and I'll show you how, with digital, or we can represent it analog. With analog, the way it represents it is that this is, say, a magnetic tape. This is North Pole, and this might be South Pole. In other words, we magnetize the tape North Pole or South Pole. And this is differing degrees. So as time goes on, and as the tape physically moves past the tape head, we've saturated the magnetic domains a lot, a little, none, reverse saturation, right? Okay. So we're actually nuancing the medium. Okay. Now, the signal varies continuously. An example of magnetic tape. As you degrade this signal, basically, heat or time or whatever, make those domains orient themselves randomly. As they do, the general sound of it, if you ever listen to degraded magnetic tapes, they sound like woo, 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 woo. All of the really sort of crisp sounds are gone. And that's because, of course, all the little wiggles that are close together get filled in because the magnetic head can't detect those. Okay? So as this thing degrades, you actually hear that in the signal, and you start to lose it, right? And then the other thing is, if you tape a record or a CD, the tape copy is not as good as the original copy. And this is why the record industry never had a problem really with people taping, putting on cassette tapes, DVDs even, right? Even though they sounded pretty good, they weren't as good as a DVD. People who really wanted to hear it would listen and shell out the extra money for the DVD, right? Digital storage. Basically, you convert this in a way that I'll talk about in a sec. You convert this into, it's either on or it's off. Okay, so the magnetic signal is North Pole or South Pole, right? This might be a 1, that might be a 0 or something like that. I'm sure it's not quite that simple, but that's the notion, right? And then the difference is that basically we're taking the medium, we're saturating it, right? We're not like trying to nuance it and like half saturated or 30% or something like that, right? Okay, it's just all on. When it's a bit, it's all on, and when it's a not bit, it's all south, right? Now, as this degrades, of course, these little things are going to fill in magnetically. This is going to, become like kind of like that, and this will become kind of like this. But can't that degrade for a long time before you can't even tell whether it was a north or south pole, right? It can degrade a whole lot more before you can't even tell the difference between whether it was an outie or an innie, right? You know what I'm saying? Yeah. Right? So that's the beauty of digital things. As it degrades, you can tell. Now, here's the deal, right? Okay, if you can copy a CD, and this is, I discovered this, right? Was that gee, the little laser in my CD player couldn't read the disc, right? Well, guess which one can? The one in my computer can, right? So I can copy that CD that I can barely read with my stereo, right? I can copy the thing, and the copy plays just fine. Right? The copy is exactly identical. The computer just sits there and grabs all those bits off of there, right? And it makes an identical copy. And this is why, of course, the record industry really doesn't like CDs so much, right? And MP3s especially, the copy is the original, right? It's exactly the same, right?
Are they trying to transition back to magnetic tape?
No, but they're putting all this digital rights. In fact, Sony did a little thing where when you stuck a Sony CD, in your computer, it installed DRM software on your computer. Some people had, like, I don't know, maybe the ACLU or something like that, had problems with that, This installs software that you imagine that, right? Basically, it was a virus, Okay. And then the cool thing about digital storage is you can actually incorporate into the whole scheme error correction. And so like DVDs have this on it, so even though it's much more data density than a CD, they've actually got algorithms to get back bits that they lose, yeah.
How long does it take for something digital to degrade like that?
Much longer. I don't know. It's not infinite, right? CDs have aluminum in them, right? And so they're just now sort of thinking, well, gee, they have come delaminated. They do fail, right? But it's not forever. But it's a lot longer, right? Then that's the question, right? What do you do with information like kids' pictures? Where do you put it so that, right? So that you never lose it. If you put it on 3.5-inch floppies, you already can't read it, right? You know, so where do you store it, right? Probably the thing to do is set up a Google account and mail it to yourself, you know? Or without joking, just store it on a network, right? Because the network's always going to be upgraded, right? This is an example. The gray line is an analog signal. We're representing it in a very bad way with the red line there, okay? Notice that the red line, there are two aspects that make the red line not very good. Okay, the first is that we're trying to represent a continuously varying thing with 8 different levels. 1, 2, 3, 4, 5, 6, 7, 8 levels. So apparently we have 3 bits to work with. This is 3-bit depth. Okay, so the depth, we talk about depth and we talk about sampling rate. This is sampling rate, this is depth. This is 3-bit depth. Okay, CDs, and do you see that because we only have 3 bits, we can have 8 different numbers, right? Do you see that's what part of what makes the red line a crappy copy of the gray line, correct? Yeah? Is that we've got so much chunkage this way. Well, what if we had 16 bits? If we had 16 bits, and that's what CDs have, okay, per sample, well, 2 to the 16th is what? Is that 65,536, is it?
Yes.
Yes, indeed it is, right? So imagine if we had 65,536 different bins this way, you wouldn't be able to tell, would you? In fact, this projector could not display that because it only has 600 pixels that way, correct? Right? So yeah, this is a very cool thing. CDs sample, the depth of CDs is 16 bits, and that's why it's better. But the second reason that it's better is that this thing is sampling maybe once every 1/10 of a second, or who knows, I don't even know what this time scale here is, right? Okay, CDs sample about 44,000 times every second. And so if you imagined that we went up to this line thousands of times in this space, right? And we had 65,000 different heights that we could go to. I don't think you could tell, certainly not with this projector, right? I don't think you could tell the difference between the digitally represented line and the real line. Yes? I'm thinking now we have several questions. Question 1.
So, Jordan, Raphael kind of put it to me, is this a lot like reasons in calculus where you take like...
I think so. Yes, I do believe. Yes. Okay, it has to do with, because basically as every bit you add is another yes-no type thing, right?
So,
comparison.
Make sure to multiply by the length of the
CD doesn't see it like that. Like, it doesn't look at the area or anything like that. It just looks at the height and said, okay, this correlates with this sound, like that.
No, basically the CD represents numbers. The CD is actually just data, right? A CD is raw data. It's actually numbers, and it's sampling every 44,000th of a second. It says, okay, the voltage should be this. And it's got 65,536 voltages that it could be, right? And every, 1 over, 44,000ths of a second, right? It's telling you what the voltage should be. David?
So 2 questions. One, each like square on the graph is
Uh-huh.
digital off on percent.
No, it's a binary number. We're representing 8 different numbers with 3 bits because it's binary, right? We don't need 8 bits, we need 3 bits. Yeah? So
Okay.
16 bits would give us 65,536. So there's a little machine in there, a computer on your CD player, right, that's converting the binary to a actual voltage, which is pretty simple actually. Yeah?
Is this similar to like a bit rate of a song? Or like
Exactly, yeah. The bit rate is this thing, right? Okay. And, well, actually, the bit rate for an MP3 when you're compressing is a combination of both, right? It's a combination of both. Increasing both increases the bit rate. Yeah.
So how is it physically represented on the disk, and how does the laser read it?
I know. Yeah. You're the guy, right? So here's a sine wave with 10 samples, 25, 50 samples, 200 samples, baby, right? What's going on vertically? I don't know, right? So CDs sample really, really fast, right? And then the question is, what's going on the, how does it actually do it on the disk, right? Okay, on optical disks, and they're all about this, right? And this is on your little note guide. What they have are pits, like this, okay? They've got pits, and the laser can read these pits, and what it does is they've set it up so that when the laser goes down into that pit, it sets up maybe destructive interference, or destructive versus constructive interference. And I'll pass this around. This has sharp metal on it. I cut myself on it last year, so be mindful of how you handle it. Since the computer is not on right now, we've got to eject the disk manually. There's a little thing there, right? You can pull the disk out, right? There's a little motor that does this, right? And then here is the actual laser is right here. You can see that it can move on this little precision thing there and read the bits off of there, right? And I'll pass that around, and you can Oh, and then